Welcome, everybody. It's my pleasure to introduce Florian Frick, and today he'll be telling us about RIPS complexes, projective codes, and zeros of odd maps.
Yeah, thank you. I'm glad to see that this seminar has succeeded in bringing together people from different mathematical backgrounds and different communities. And we've seen a bunch of connections and applications of RIPS complexes and their variants already. And today I want to add a few to this list of connections and applications. And to adequately explain how RIPS complexes tie into the stuff that I'm interested in, let me try to present you a mathematical storyline that I'm invested in. And this mathematical storyline could be summarized as every mathematical problem is a topological nail, right? So if you come to me with a mathematical problem in analysis, combinatorics, about some random structure, whatever, then my go-to response is to think that you're trying to trick me and you're just, you're speaking in tongues in the language of your field. And actually what you've given me is a topological problem. I just have to expose it as a topological problem, and then I whack it with my topological hammer and until it gives way. So that's my day job. Or to give you an example that I'm sure many of you are familiar with, if you have D continuous probability measures on RD, mu1 through mu d, then you can bisect them all by a hyperplane. Yeah, so if you have 3 blobs in R3, then there's a nice 2-dimensional plane that cuts all of them precisely in half. And how do you solve such a problem and many related problems? What you do is you come up with the space of potential solutions. So I have that here as step 1, potential solutions, sigma-like solutions. You parameterize the space of solutions, in this case, oriented hyperplanes that might bisect your measures. Step 2, you come up with a map tau, like test map, that measures to which extent the potential solution deviates from an actual solution, meaning tau is 0 if and only if your problem has a solution, right? See this tau, you put in a hyperplane, an oriented hyperplane, you measure what's on the positive side of it, what's on the negative side of it. If it's the same for every measure, you're done. So if this map is 0, you're done. And then you have to exploit something about the map to show that it actually has a 0. In this case, this map has a nice symmetry, and you can use the Borsuk-Ulam theorem that tells you, any map from a sphere to RD with an antipodal symmetry must have a 0. And it just so happens that the space sigma up to compactification is a sphere. So that's a general strategy, just to summarize this common strategy on one slide. To solve any problem whatsoever, what you do is you parameterize the space of potential solutions. You define a map that measures to which extent the potential solution deviates from an actual solution, and you hope that you can show that this map has a 0, and then you're done. Okay. So just to give you one more example from the realm of topology, if you ask the question, here's my nice compact manifold M, and I want to know, does it embed into RD, Euclidean space of dimension D? Maybe you're tempted to say, okay, my space of potential solutions is all the continuous maps from M to RD. Don't do that. Instead, fix a continuous map, F from M to RD, and now try to obstruct that it is an embedding. And how would you obstruct that a map is an embedding? You take 2 distinct points and you see whether they map to the same point, then it can't be an embedding, right? So the space of potential solutions, potential obstructions in this case, is the ordered configuration space of 2 distinct points in M. Your test map measures whether f of x is equal to f of y. And does it have a 0? Well, that's the question. Is there an odd map? By odd, I always mean a map that commutes with a Z-mod 2 symmetry. Is there an odd map into RD without 0? And the main obstacle in this approach is you have to understand the topology of this space of potential solutions well enough to know whether any map that occurs as a test map has a 0. Right? And these are what I will call Borsuk-Ulam type theorems. Okay, so how does the concept of RIPS complex tie into this mathematical storyline. Well, Rips complexes, they're just configuration spaces of nearby points, right? So I maybe interpret what I wrote here as a simplicial complex, right? So I take all sets, maybe you want finite sets, I don't care. Take any set in your metric space X such that pairwise points are distance less than epsilon, right? So that's a space of nearby points. They deviate at most epsilon from each other. So when you encounter a problem where the space of potential solutions should be sets of nearby points, then your sigma is a Rips complex. And you need to understand the topology of a Rips complex to solve this problem. So to give you one prototypical example here, if sigma is your space of potential solutions to a problem, oriented hyperplanes, distinct points, whatever, but you're in a situation where unfortunately there is an odd map from sigma to RD. You can't show it has a zero. You lose, right? That avoids zero, right? Then what you could still hope is that perhaps for some small epsilon, if you take the Rips complex of this suddenly is rich enough that such a map must have a zero. And what does that mean? Well, if you can't expect a solution to your problem, maybe you still have an approximate solution. If in R3 you don't have 3 blobs, you have 5 blobs, well, maybe there's not a hyperplane that cuts them in half, but maybe there's an approximate way of cutting them in half by looking at the Rips complex, in this case, of a sphere. Okay, so now, okay, I could, give you all kinds of examples of this. What I'll do instead, I will immediately attack the end boss, so to say, because the usual way of then using the setup is to use the Borsuk-Ulam theorem or one of its versions, many generalizations and what have you. So recall the Borsuk-Ulam theorem says any odd map from the d-dimensional sphere to d-dimensional Euclidean space must have a zero. Now, again, by odd, sorry, I didn't mean to erase this actually. By odd, I just mean this, right? And if you now want results about approximate solutions, you want an approximate Borsuk-Ulam theorem. So you want to prove results of the following form. Suddenly, your Euclidean space is larger. Instead of r to the d, it's r to the d plus k. You have less degrees of freedom than parameters you want to measure. And of course, an odd map from SD to RD plus k has no reason to have a zero. Any generic map will avoid zero. But we want to prove results of the form there are nearby points in the sphere such that they average out to zero in this sense. A convex combination of their function values is zero. So that's one goal we could have. Compare this to this theorem, classical theorem of Young from the 50s that does the other case, basically. If you map to RD minus K, if you have more degrees of freedom than things you're measuring, you expect many solutions. And that's in fact true. This has homological dimension at least K, the zero set of such a map, right? So Young and then Gromov with his waves of the sphere theorem later showed that this k-dimensional set of zeros behaves geometrically like a k-dimensional equator of a sphere. Okay, so that's the case of mapping to lower dimensional Euclidean spaces. We're mapping to higher dimensional Euclidean spaces. Yeah, so here's this again, our goal. We want to prove results of this form. Let me rephrase them a little bit, just so I can tie one more thing into this, one more topic. The rephrasing is, take a d plus k dimensional vector space of odd maps from SD to real numbers. Whatever your favorite odd maps are, maybe odd polynomials, right? Then there is a small, where we have to quantify small, and maybe in terms of the diameter of the set. Then there's a small set in the D sphere such that no map in this vector space V is positive on all of A. Right, so you can't stay positive on this set. The set is too large. Since you're an odd map, you have to turn back at some point, and we want to quantify how large does a set have to be that I can witness this turning back, that you can't Not every map in your vector space can simultaneously stay positive on A. So as one example, again, compared to this theorem of Babenko, if you have a trigonometric polynomial from the circle to real numbers, right? So these are trigonometric polynomials of degree n, then they cannot stay positive on any closed circular arc of some given length. Right? So these are the types of results we're interested in. Okay, and before I go on and give you the results that we can actually get here, let me just pause for a few seconds and see if people have questions, concerns, complaints.
Could you move the last slide up a little?
Oh, sorry. Yeah, I could.
Thank you.
Okay. So let me give you actual results. So this is joint work with Henry Adams and his graduating student, John Bush. So here's one result of this form. Just to, I should say I didn't choose the most tedious statements. I tried to keep it as simple as possible so that people can follow along and ask questions and make comments. So if V is a 2n+1 dimensional vector space of odd maps from the circle to real numbers, then there is a set A in the circle of diameter at most 2 pi times n over 2n+1, such that no map in V stays positive on all of A. Every map has to turn back. This theorem is optimal in the following sense. I put here in green what I mean that it's optimal, meaning for any set of a strictly smaller diameter, there is an odd function that stays positive on all of A, and this odd function is a raked trigonometric polynomial of degree at most n. So what's a raked trigonometric polynomial? It's one where every second term is raked out, right? So only odd degrees in the trigonometric polynomial, thus these maps are odd. They show that this is optimal. That's actually, and that is something that is quite tedious. So what comes into this is you study the convex hull of this so-called symmetric moment curve. So you write down sine t, cosine t, 3t, and so on, the odd ones. The convex hull of this is the Barvinok-Novick orbitope. That's the name of this object. We don't really understand what this looks like. That's one problem. But by Hahn-Banach, what you can do is you can just study, call this curve gamma. You can just study inner products of gamma of t with a fixed vector that parametrizes all raked trigonometric polynomials, right? Take the inner product of this with a fixed vector, that's just coefficients multiplied with this and added up, which convinces you that raked trigonometric polynomials are actually non-zero ones, are actually parameterized by a sphere. So that sounds like there's some Borsuk-Ulam phenomenon going on here. And then you have to show that any set that's small enough can actually be separated from the origin by a hyperplane, and that would show the optimality of this. And as I said, that's non-obvious, and at least to us, we came up with a somewhat tedious proof of this. As one example, just to see what's going on here, suppose you have 5 odd functions from the circle to real numbers, linearly independent if you like. Then you get a set of size 2 pi times 2 over 5, such that there is no f in your vector space, no linear combination of your 5 functions that is positive on all of A. And the reason for this is what I tried to indicate here by red points. It's this diameter is precisely the diameter of this regular pentagon in the circle. So the circle has an efficient packing by metric balls. My claim is that's what's really behind this. Let me try to explain this. So how do packings by metric balls come into this? So define this parameter here. Given a metric space, let Pn of x be the largest epsilon that you can choose, such that you can find n points in your metric space that are pairwise at distance at least epsilon. So the picture you should have in your mind is, here's your space X, and you try to pack epsilon half balls into your space X that are pairwise non-overlapping, right? That's what you're trying to do. What is the largest epsilon such that you get these epsilon half balls as a packing of your metric space X? And then the theorem that we can prove is, if you have an n-dimensional vector space of odd maps from the D-sphere now, so not just circles, D-sphere, to real numbers, then there is a set A in the D-sphere of diameter at most pi minus, Pn plus 1 of real projective space of D dimension, such that every function in your vector space, for every function, the restriction to A does not stay positive. Yeah, so packing of metric balls in projective space sounds abstract, but is something very easy, right? Recall projective space is just lines in Rd plus 1. So what are you trying to do? To compute this parameter, what I'm asking you to do is put n plus 1 lines through the origin in Rd plus 1, and do it in such a way that the minimal angle is as large as possible. And that's what this is, right? And then subtract that from pi, and that's exactly the parameter you want. Maybe I should, linger on this slide for a second, see if this makes sense to us. So let me try to explain this maybe in words. What is this phenomenon that I'm trying to get at here? It's, if you have odd maps from a sphere to real numbers or to Euclidean space, at some point they have to turn back, right? They can't always be positive. They have to be positive half the time and negative half the time. So they have to turn back. How fast do they have to turn back? On sets of which size do they have to turn back? Well, that's precisely dictated by packings of metric balls in projective space, or equivalently angles between packings of lines to the origin in Euclidean space. Right? That's exactly what tells you what this behavior is. To prove this, okay, I like metric versions of Rips complexes more than Rips complexes. So one version that, I believe there are many versions of this, but one version that Henry and Michael Adamaszek and I introduced what we call metric thickenings, which is the following thing. X is a metric space, and perhaps I want it to be a nice metric space, a so-called Radon space, which means, this technical condition, every probability measure can be approximated from the inside by compact sets. Then define the following thing: probability measures on your space whose support has diameter less than epsilon. My claim is that's a good version of Rips complex, which has the added advantage of coming with a metric. Namely, you can just use the optimal transport metric on this, right? So to determine what the distance from one probability measure to another probability measure is, you just take out your wheelbarrow and you want to transport this measure, these heaps of dirt, to these heaps of dirt, and how much work do you have to do this? That's the distance. Okay, and is this a good version? Yeah. So Henry's graduate student Michael Moy proved, if X is the totally bounded space, then the persistence diagrams of Rips complexes and the persistence diagrams that you get from these metric thickenings, they're actually identical. So if you're interested in persistence diagrams, it comes out to the same thing.
And Florian, let me interrupt just to say that Facundo Mamoli and his student Qingsong Wang have an independent proof of this theorem as well.
Oh,
so this is all very recent, and there's no way you could have known that. But
I see. Oh, good, good.
I just want to put it on YouTube.
No way that I could have known that. That's good.
No way, absolutely no way. Yeah.
That's good news. Yeah, great. That's fantastic. So how do we use this concept? How does this come into this? So what I want to show you is packings of metric balls and zeros of odd maps, they're related. And we only know that through the mediary of Rips complexes or their metric versions. Right? They come into it to somehow negotiate between these two. And how does this go? It's actually not that difficult. Let me give you a feeling for how this goes. Take some parameter delta that's larger than pi minus this packing number of projective space. And I want to convince you that there is an odd map from Sn, where this n here is this n. How many points, -1, can you pack into your space such that they're pairwise at distance, delta. I shouldn't say delta, pairwise at distance, whatever this is. Then you can map this in an odd way to this metric thickening of the D-sphere, where all the measures have support whose diameter is less than delta. How do you do this? Well, let's call this packing number alpha, this parameter. Find a bunch of points that achieve this packing. They have pairwise distance at least alpha. Lift them to the D-sphere. So for every point you get 2 copies, plus and minus. Think of Sn as the boundary of the cross polytope. So take the standard basis and their negatives and then the convex hull of this. Now map the standard basis vector I to xi plus and negative ei to xi minus. And you can, this in some way, in a natural way, gives you a map because you can extend what I called in quotation marks linearly. We're mapping to a space of probability measures, but just think of it as living in the space of signed measures, and then you can naturally write down a map and you check it works. Right? And why does it work? Well, every point is at distance at least alpha from every other point, meaning, so here's your point xi. It's at this, meaning its antipode is at distance at least alpha from every other point. But if that means there's an alpha ball down here that sees no other point, meaning every other point has to be in the pi minus alpha ball up here, right? So that's the proof. What this shows more generally is that if this packing number, if there's a packing by n+1 metric balls of diameter of radius, sorry, alpha half in RPD, that's actually equivalent to, there is a linear map from Sn to this metric thickening of Sd at scale parameter delta for any delta that's larger than pi minus alpha. So thinking of codes in projective space, right? Some people call these codes, things that pack nicely into projective space. Codes in projective space are exactly the same thing as linear maps from spheres into metric thickenings. So there's no difference. Meaning, so a linear map is a special case of an odd map. Right? A linear map is not just negative x has to go to negative f of x. There's more, right? There's some linear structure, which means the Z mod 2 equivariant topology of this metric thickening of this space of probability measures, this actually can obstruct the existence of linear maps. So you can think of the existence of odd maps from spheres into metric thickenings as some kind of topological analog, some topological relaxation of the existence of projective codes with distance alpha of size n+1. My question for you is this obstruction complete? Is it true that whenever you have an odd map from Sn into the metric thickening, that you can actually find a linear map and thus a projective code? I don't know the answer to this. I guess if I had to guess, then yeah, maybe I don't want to guess. But,
and Florian, let me interrupt with a clarification question on the last slide. So this is from Alexander Kirisev. So he asks, do you mean d-dimensional projective space instead of the sphere?
At which point?
I think you're using them both. You're starting in the projective space RPD, you have these points, and then you lift them to antipodal points in the sphere.
Right. And now I really want to think of the domain Sn, right? This thing.
Oh, I
boundary
see.
of the cross polytope. Right. Yeah, so I think all the SDs and RPDs and SNs are in the correct place here.
Yeah,
Okay.
yeah, he agrees. Yep.
Good, good, good. Yeah, no, but please do ask clarification questions. Yeah, so is this actually a complete obstruction? Can you actually tell whether projective codes exist in this way? I mean, you can. You know, this would be nice if we could, you know, just say instead of projective codes, we can just study the topology of this space and it's exactly the same. Right now, we just know it gives bounds. Okay, so I hope I've convinced you that projective codes, packings, bimetric balls, lines whose angles are as large as possible, however you want to think about it, these things give you lower bounds for the topology of metric thickenings or Rips complexes of spheres, whatever you prefer, however you want to think about it. So maybe I should at least give you, you know, one result about projective codes so that you can see if this is a useful relation. So here's one such result, and of course I chose the result of my colleague Boris Buch and his former graduate student Chris Cox. Define this parameter theta dk. What is theta? Well, you minimize over all sets of unit vectors in Rd of size d plus k. And what do you minimize? The maximal inner product in absolute value between points. Yeah, so it's exactly this concept of lines in Rd, and you want to maximize the minimal angle. So so you're exceeding the dimension by k. You have k more points than dimension. Then this parameter is bounded from above by 1 plus little o of 1, and then 2 root of k plus 1 over d. They also prove better results, but for simplicity, I'm stating this one. This little o of 1 is as d goes to infinity, this goes to 0, right? That's what I mean by this notation. So what is this telling us, right? If you work this out, what does this mean? It means if you fix your favorite positive integer k, and you ask the question, when is there an odd map from SD plus k into metric thickening of the D sphere or Rips complex of the D sphere at distance parameter delta? When does this exist? How fast does this occur? Right. So as you grow the distance parameter for Rips complexes of spheres, you see the sphere for quite some time. And at some point, you get to the distance parameter where you have an inscribed regular simplex. And then the homotopy type jumps up. Right? Question is, do you have to go for much longer to see other homotopy types? And the answer is no. What this result tells you is, as soon as d is larger than pi half, as soon as you're a little below the equator, you can go a little below the equator. If the dimension is large enough, you immediately get this. So the homotopy type of Rips complexes immediately explodes. Okay, so that's the one relation. Projective codes imply lower bounds for the equivariant topology of Rips complexes. Similarly, you can show that zeros of odd maps give upper bounds. So to give you an idea of how to prove the result that I advertised, I need a second step here, which is the following. Take a free Z-mod 2 space. So if you like, think of X as the D sphere. V, an n-dimensional vector space of odd maps from your metric space to real numbers, such that whenever you pick a set of diameter at most delta, there is a function in your vector space that is positive on your set A. There's some function that separates A from 0. Then there's an odd map from the metric thickening at distance parameter delta to the n-1 sphere. I write down this proof here just to convince you that it's easy. You just write down the basis of your vector space, and essentially you just integrate the spaces against any probability measure in your metric thickening. And then you say Hahn-Banach, and then you're done, right? Hahn-Banach meaning any convex set can be separated from the origin. If a convex set doesn't contain the origin, then there's a hyperplane that separates it from the origin. And that's all you need. So again, let me give you an example of this. So Henry, together with Michael Adamaszek, determined the homotopy types of Rips complexes of circles. You start out with a circle, and then as the distance parameter increases, it jumps up to S3, and then S5, S7, goes through all the odd dimensional spheres. And where are these jumps are at the diameter of regular odd 2n+1 bounds. Right. So as an example, so an example has actual numbers, I guess. Take delta to be just a tiny bit larger than the diameter of the regular pentagon. Then the Rips complex, or the metric thickening of the circle, is S5 up to homotopy. If you write down your favorite vector space of dimension 6 of only odd maps, so here's mine. All of these are odd maps from the circle to real numbers, 6 of them. Then the following is true. For every A in the circle with diameter less than this, there is, well, linear combination of these, meaning a raked trigonometric polynomial of degree 5 that is positive on A, that separates A from 0. Okay, which means I think I've completed it. I've shown you projective codes give lower bounds for the equivariant topology of metric thickenings, equivalently Rips complexes of spheres. And these in turn give lower bounds for zeros of odd maps and thus Borsuk-Ulam type results. And I wouldn't know how to prove this. I mean, projective codes and zeros of odd maps, they're somehow related. How you would do this without this intermediate step is unclear to me. Well, I have at least 2 more minutes, I think, so I'll say a few more things. Notice that packings and coverings are related, right? If so, a very crude bound for packing is a volume bound, for example, right? Is it perhaps true that if you add up the volumes of these metric balls, you get more than the volume of the space you're trying to pack? Then you're in trouble, right? So that's a way how packings and coverings are related. So if you have a covering of RPD by metric balls, so I have these n midpoints of metric balls of radius d, and they cover RPD, then I can actually use this to write down an odd map from this metric thickening or Rips complex to an n-1 dimensional sphere. Meaning, well, if I can do this, then suddenly I've sandwiched the topology of Rips complexes between packings of projective space and coverings of projective space. I can make this precise. So here's the precise thing. An alpha packing of RPD of size n+1 tells you that the cohomological index, so some measure of cohomological dimension, is at least n+1 for such delta. And an alpha covering of size n+1 gives you an upper bound on this cohomological index for such delta. So that means studying the topology of Rips complexes is really difficult, even of spheres. I have problems at the end, I think. Let me try to state some problems to, oh, yeah, I mean, maybe I'll just flash this slide at you as one example of what you can get out of this machinery, just to get something that's not related to this. If you have an embedding of a D sphere into Rn, then if you want to see how generic it is, you could, for example, prove there's always a set in the D sphere of diameter less than delta, where delta is larger than this, such that the convex hulls of f of x and f of negative x intersect. And so that tells you something about how generic an embedding of a sphere into Rd can be. At some point, antipodal sets have to have intersecting convex hulls. So if you map the circle into R3, then there are 2 antipodal sets of diameter 2 pi over 3 whose convex hulls intersect, as one example of this. Okay, so let me start out by asking one question that I'm not sure if it's on the slides, which is, so here's a question. I hope I've convinced you that the topology of Rips complexes of spheres, that's a topological analog, a topological relaxation of projective codes in projective space. Now, there are all kinds of bounds for codes in projective spaces, right? Lower bounds immediately translate to this because of the relation I showed you. What about upper bounds? Take your favorite upper bound for projective codes. Is it also an upper bound for the topology of Rips complexes? Is it also an upper bound for Borsuk-Ulam type theorems, zeros of odd maps? How far can you push this up the ladder up this hierarchy of mathematical topics? We can do things about the circular chromatic number of graphs. This is just, in case I was really fast. Here are some problems. One problem that I think is interesting, but maybe I've convinced myself and hopefully you that it's incredibly difficult, is determine the asymptotics of this cohomological index, or whatever your favorite notion of dimension is, of Rips complexes of spheres if you fix the distance parameter and you let the dimension go to infinity. Right, so maybe fix distance parameter 2 pi over 3. Now look at the Rips complex of the 3 sphere, the 4 sphere, the 5 sphere, and so on at this distance parameter. What is the, let's say, cohomological dimension, cohomological index of this object? How does it grow? It's definitely exponential, I think. Is it super exponential? Probably not. What is the correct growth here? The other thing that I think is interesting is zeros of maps are related to designs. Determine the relationship between the equivariant topology of Rips complexes or metric thickenings of spheres and the size of what I will call projective designs. And not only I call it projective designs, everybody calls it projective designs, but let me tell you what it is. It's the following that seems very much related. If V is a k-dimensional vector space of maps from RPD to real numbers, they're not odd or anything. Odd maybe doesn't even make sense here, right? Find as few points as possible in projective space such that the average of every one of your functions is the average over just these points. These always exist, funnily enough. How large are they? This is very much related to what I've talked about. If you're saying, isn't it exactly what you're doing? No, it's not quite, because we're looking at odd maps from spheres into Euclidean space, right? Their integrals are always 0. They always average out to 0. And now we're trying to find points that show that they average out to 0. You could take x and negative x, that always averages out to 0, but you're not allowed to do this. You're trying to find a few points that whose average is 0. Okay, so these are some problems I find interesting, and maybe with that I should stop and see if people have comments and questions. Thank you.
So before we get to questions, let's briefly unmute ourselves and applaud for the speaker. Thanks, Florian, for the great talk. What questions do we have?
I'm told you need to ask at least 15 minutes of questions.
Parvana, please go ahead.
Sorry, why do you take the k-dimensional subset of the functions on RPD?
Oh, if you take all functions on RPD, you have an infinite dimensional vector space, and there's no hope of finding such a thing, right? And an averaging set or design always has to be tied to your favorite functions. So on the sphere, people take polynomials, for example. They take polynomials of total degree at most t, and then they want to find a few points on the sphere, such that if you evaluate your polynomials of degree at most t on these few points and average them, that's exactly the average of the function over the entire sphere. Right? So the idea is you can average a function over a space by only averaging over a few points. If you want to do this for every function whatsoever, that's not possible, right? But if you restrict to...
Yeah, is it somehow that the solution to this optimization might depend on the dimension of the subspace that you are choosing?
Oh, it definitely will. Yeah, of course. Yeah.
And
So
is
this
there
is
any relation with duality of the function space and the measure space?
a
So
duality.
here you take the functions and
Mhm.
it might be that this is just the dual product of the function.
So I can, right, I can pair measures and functions, right? So this is a primal dual pairing.
Yeah.
Right? And I'm trying to compute these functionals by just averaging on a few points. That's true. I'm not sure if that insight helps in understanding the asymptotics of, I want to understand how does n grow in k, right? That's what I want to understand. Yeah, so for spheres, there's this recent breakthrough, right? That we understand how spherical designs grow in, if you take polynomials of total degree at most t, how many points do you need to average every polynomial of total degree t over the sphere? And it's polynomial in it's t to the dimension.
And
Yeah,
can
Florian,
you also, sorry,
Go
you
ahead.
go ahead. I just wanted to see that, can you just elaborate how this space or set of odd functions looks like in the whole space?
Oh,
At least for the finite set.
I'm not sure I understand the question. So
We have we have the space x, and the whole function space would be r to the power of x, and you just take the odd functions. How does it look like in this vector space?
I'm not sure that we should try to visualize this, right? But it's some kind of Z mod 2 invariant subset of it. Yeah, I'm not sure what the answer would be, since it's an infinite dimensional object in another infinite dimensional object. So even if I go around with my topological hammer, I'm not sure that I want to actually think of this as a geometric object.
Yeah, okay, thank you.
Yeah, sure, thanks.
And Florian, I was
Hey,
going to
John.
ask it, can we see the chromatic number stuff, the circular?
Well, I'm glad Anton is here to ask this question. Yeah, briefly, I'll say something about this. So if you have a graph of vertices and edges, what you can do is you can place the vertices on, by RP1, I just mean the circle of circumference pi instead of 2 pi, right? Such that two endpoints of every edge are at least, let's say, pi over r apart, where r is your favorite positive real number. The infimum over all r, such that this is possible, is what we call the circular chromatic number. So you want to place the vertices on the circle such that whenever there's an edge between them, they are as far apart as possible. So edges repel vertices. And the furthest they can be apart, that's called the circular chromatic number. And this is one of these combinatorial problems that's clearly a topological problem, right? And the reason it's a topological problem is because you can come up with this thing called the box complex. It's a simplicial complex, maybe in this case, I wanted to draw it for you. What is it? It's a simplicial complex on vertex set and a copy of the vertex set that's disjoint from it. I'll think of this as positive and negative vertices. And then I put in a face for, this face sigma 1, sigma 2 is in my box complex if every vertex in sigma 1 is connected by an edge to every vertex in sigma 2. So in this example, this box complex is a subcomplex of the cross polytope on 3 plus 3 vertices. And actually, you can convince yourselves what it looks like is it's this simplicial complex in this case. It's homotopy equivalent to a circle. And the topology of this box complex gives lower bounds for chromatic numbers and for circular chromatic numbers. There's a theorem by Simonji and Tardosh. If there's an odd map from an odd dimensional sphere into the box complex, then the circular chromatic number is at least 2n. And that this is an odd dimension here is crucial. And that's not clear from the definition of circular chromatic number, that this is crucial, that there should be an odd dimensional sphere here. What I'm saying is Rips complexes of circles explain why this needs to be an odd dimension, because Rips complexes of circles only see odd dimensional spheres. They skip the even dimensional ones. And what's the relation? The relation is roughly this. If you have a circular coloring of your graph, you already know where the vertices go in RP1, and now you know why I want to think of it as RP1, because I want to lift it to the circle. Every vertex gets 2 copies, V and negative V in the circle. But V and negative V, that's precisely the vertex set of my box complex. So now I extend this map in a natural way from the box complex to, and instead of in the circle, I land in some Rips complex of the circle. I check this is an odd map, and this gives me topological obstructions to the circular chromatic number. So in particular, we can give a new proof of this result. I should warn you that these 3 lines, while I think they're morally correct, they don't really give a proof. There are a few more insights needed to actually turn this into a proof. I could ask one more problem about this, which is the following. Suppose if you now color a graph, instead of with points in S1, you color it with probability measures in S1, whose support has diameter at most delta. If delta is 0, that's a circular coloring. If delta grows, you're allowed to spread out your probability measures. Every point gets a probability measure that's a little more spread out on the circle. Adjacent vertices receive measures that are at least r apart in the optimal transport metric. Prove lower bounds for this. Why is this interesting? For delta equal to 0, it's the circular chromatic number. As delta grows, you get closer and closer to the usual topological lower bounds for chromatic numbers. And this is some kind of interpolation, right? That tells you that these topological lower bounds for chromatic numbers, they tell you something about optimal transport along the circle. That's constrained by a graph.
Florian, can you explain that transition again? So the circular chromatic number is in some sense sharper than the chromatic number. So is that what you're saying, that as you spread out these measures, you go from the circular chromatic number to the chromatic number? And how do I see that?
Sorry, no, you go the other way. So there's a chromatic number, and then the circular chromatic number, and then there is the, let's say, Z2 equivariant topology of the box complex. And what I'm saying, what I'm suspecting is, I haven't done this, that's why it's a problem, not a result. What I'm suspecting is, as you go from circular chromatic number and you spread out measures more and more, you get closer and closer to the topology of the box complex.
Florian, I wanted to ask a question. So the first problem that you gave on the, I guess the following slide, or right? So here you're fixing a scale and considering that asymptotics as a dimension goes to infinity. Do you think these types of stories might shed any insights on sort of the dual question of fixing a dimension and then letting the scale grow?
Sure, I'm not, yeah. I'm not sure which one is more tedious. Both are interesting. The reason that I formulated it this way is because I previously presented this result for projective codes that did the same thing. You're right that, of course, one should also fix the dimension and let the scale parameter grow and see what, where are the jumps from, the dimension is linearly larger, is polynomially larger, is exponentially larger than the sphere you started with.
But you sort of think of that as sort of equally hard, potentially.
Yeah, I'm not even sure that I'm the right person to ask. They're equally hard for me.
Further questions for Florian? Well, if not, thanks again for the fantastic talk, and really appreciate it.